continuing on with the normal distribution, pretty much every set of data that's normally distributed has that bell-shaped curve, will have a unique mean and standard deviation. What do we do if we have a population that's normally distributed, but does not have a mean of 0 and a standard deviation of 1? We don't have a table for every situation. So to make our calculations less complicated, we've got a way of standardizing values with z-scores. So basically we're going to scale the actual values we have so that they fit on our table. Whatever the mean of a particular distribution is, we're going to scale it so its mean is 0. That way any value greater than the mean will have a positive z-score, and any value less than the mean has a negative z-score. The z-score itself is how many standard deviations above or below the mean a particular value is. Say we have a test score with a mean of 80 and a standard deviation of 5. A test score of 85 is one standard deviation, 5 points, greater than the mean, so it would have a z-score of 1. A test score of 70 would be 10 points below the mean of 80, which would be 2 standard deviations less than the mean, so it'll have a z-score of -2. All of this can be easily calculated with a formula. So if we have a normal distributed random variable x with a mean mu and a standard deviation sigma, we're using Greek letters for the mean and standard deviation just because it's traditional, we can transform it into a standard normal using z equals the x value, the value we're interested in, subtract the mean over the standard deviation. I've always found it a little easier to remember it in words rather than as symbols, but whichever version of this you prefer to use. Yes, you'll need to have it memorized for the test. We're going to use z-scores to standardize the values we're interested in into values that we can then use the standard normal table for, and then find the probability of getting a value in a particular range. Okay, let's go straight to an example and think you're going to see this is not all that complicated, especially now that you've had some practice using the standard normal table. So what we're going to do is we'll have a large manufacturer of light bulbs that have a life expectancy of a mean of 75 and a standard deviation of 80. So the interesting thing about this is we can find all sorts of information out, and all we need to know is that it's 1, normally distributed, 2, what its mean is, 3, what its standard deviation is, and we can find out all sorts of different probabilities. So we want to use a standard normal distribution, find the probability that a light bulb is going to last between 750 and 930 hours. So we know this population of light bulbs has a mean lifespan of 750 hours. We're interested in a particular light bulb having a lifespan between 750 and 930. Again, this is a number line. 750 is right in the middle of the distribution because that's its mean. 930 would be to the right of 750 on a number line. And then what we're going to do is take these two values, 750 and 930, and scale those values to be z-scores. We're going to use our formula. So our mean is 750, our standard deviation of 80. So the first z-score, we're going to take 750, subtract the mean, which also happens to be 750, divide by the standard deviation, which was 80. That gives us 0 over 80, and 0 divided by anything is just 0. So this particular value here matches up with a z-score of 0 on our standard normal table. Remember all those earlier problems we did? We always had a 0 here in the middle, so 750 corresponds to that. Then we'll take the 930, we'll get a z-score for it, so the 930, subtract the mean, which is 750, divide by the standard deviation, which is 80. Simplify, we get 180 over 80, which is 2.25. So the light bulb lifespan of 930 hours corresponds to a z-score of 2.25. We're trying to find the probability of being in this interval here, which is going to match up with the area under the curve here. And we can find that area by looking up these two values in our table. So when we look up 2.25 on our table, we'll find a probability of 0.958778. When we look up 0, we'll find a probability of 0.5. You probably could have guessed that one. And then we're going to subtract to find the area in between. And we get 0.48778. So the probability that a light bulb lasts between 750 and 930 hours is about 48.8%. Okay, so it's similar to what we were doing previously. We just have this extra step in here where we have to scale down our given values for something that will be on our table. Okay, let's do another one. Being between 790 and 870 hours. So again, our mean is 750. So 790 is larger than 750, so that will be to the right. So set in here 790. And then 870 is also over here. So I'm predicting we're going to have a fairly small probability for our final answer here. And to find that, I'm going to take the 790 and find the z-score it corresponds to. Is 40 over 80, or standard deviation of 0.5, half a standard deviation. And then our second z-score, we'll take the 870, subtract 750 over 80, and that's going to give us 1.5. So these two values I'll look up in the table. When I look up 1.5, as a z-score, that gives me a probability 0.93319. When I look up 0.5 as a z-score, that gives me a probability of 0.69146. And then I'll subtract those two values, because what I'm interested in is the area in between those two values, in between 790 and 870. And that's corresponding to a z-score of 0.5 and a z-score of 1.5 with a mean of 0. And then subtracting those two, I'm getting 0.24173. So the probability light bulb lasts between 790 and 870 hours is going to be about 24.2%. Okay, probability light bulb's going to last more than 810 hours. 750 is average. 810 would be over here. Be more than 810 would be the area out in the tail of the bell curve here. So when I find the z-score for 810, the value I'm interested in, subtract the mean, divided by the standard deviation. 60 over 80, so that would be 3/4, 0.75. I'll look this up in my table. So I'll look in the z column for the 0.75, and that's going to correspond to an area at 0.77337. But that 0.77337 is the probability being less than 0.75. And we're interested in being greater than 0.75. So I'll need to take 1 and subtract the area I don't want to get the area I do want. So there's about a 22-23% chance that a light bulb is going to last more than 810 hours. one's the probability being between 730 and 850. Again, strictly speaking, drawing the graphs isn't required. It's just so easy to make a silly mistake if you don't take a few seconds to do it. Okay, so the probability being in this interval, which is represented by this area. So again, I've got two different values to find z-scores for. So that'd actually be a negative 20 over 80. So I'm getting a negative z-score here because 730 is left of the mean. So 730 corresponds to a negative 0.25 for the z-score. 750 would correspond to 0, and then 850 can be 100 over 80. That's 1.25. So in my table, I'll look up a z of negative 0.25 and find the probability that goes with that. And that was 0.40129. Write that down here. And then I'll look up a z for positive 1.25, and that gives me 0.89435. I'll take the difference of those two areas, and so with the probability being between those two cutoff values. And that gives me just under 50%, 0.49306. That's the probability being in this interval. I've got a follow-up question to this one. Say there are 800 light bulbs in a shipment. How many of those light bulbs would you expect to last between 730 and 850 hours? So my first question here was asking, what's the probability of being within that interval between 730 and 850 hours? Now I've got a specific number of light bulbs, and I want to know, of those 800, how many of them would be in this interval? So it's going to be 49% of those 800 light bulbs. So I'm going to take the 800 light bulbs times probability, multiply, and I'm going to get about 395 bulbs. So if there's 800 light bulbs, I expect a little under half, 49% of them, which would be 394 bulbs, to last, have a lifespan in that interval. And this one's a little bit different. So the manufacturer wants to offer a guarantee that the light bulbs will last at least X hours. They don't want to have to replace more than 5% of these bulbs under that guarantee. So how many hours, which number do they need here that they're going to guarantee the bulbs so that only 5% are going to burn out before then? We'd want 95% of the bulbs to last more than that. So we want to know, think of it this way. We know that the average lifespan is 750 hours. If the manufacturer guaranteed that the light bulbs would last 750 hours, half the bulbs are going to burn out before 750 hours go by, because that's the average. Half lasts longer, half lasts less than that. So we don't want this to be 750 hours. We want a short enough lifespan so that we can expect 95% of the bulbs to last longer than that value, and only 5% to burn out before then. So we're going to go backwards into our table. If we look in our table, we've got a z column and we've got a probability column. And what we're looking for in the probability column is a 0.05. Go ahead and take a look at your table, see if you can find that value. Did you come up close to negative 1.65? That's going to be the z-value we use. So if we're on a standard normal curve with a mean of 0, then at negative 1.65 standard deviations left of the mean, 5% of the data will be in that interval to the left. 95% will be greater than that. So basically we've got the z-score, and we're looking for the value of x, the actual number of hours for the light bulb. We know the z-score is x subtract the mean divided by the standard deviation. We want our z-score to be negative 1.65. We don't know x. We do know our population has a mean of 750 and a standard deviation of 80. Now we just need to do some algebra to solve for that cutoff value. So we can multiply both sides of the equation by 80. That'll give us negative 132. Here the 80s cancel. Equals x subtract 750. You can add 750 to both sides. And we want to guarantee that these light bulbs are going to last at least 618 hours. Because we expect 95% of the bulbs to last more than 618 hours and only 5% to burn out before 618 hours.